In this video, we'll discuss the implementation view of closures. So we saw in a previous video that from a functional point of view, that is to say when we're considering closures in the substitution model, because we have referential transparency, or because we assume referential transparency, that is to say, because we assume that once we create a binding for a variable, the value of that variable will never change, that we can treat closures as though we're just replacing free variables with their values. So for example, in the substitution model for multiply by, when we call multiply by with the value 2, 2 goes into x throughout the entire body of multiply by, and this x inside the lambda here changes into a 2. So the lambda that's returned has a body of times 2y. So that substitution happens in advance, and that's pretty much all we need to consider for closures in the substitution model. But let's consider what happens on the call stack once we start adding closures into the mix. So here we have again the multiply by code, and we have a global activation record, and in that activation record we have a binding for multiply by, which is this function here. Now, in the line below that it says call multiply by 2, and whatever that returns, we're going to bind that to double. So to call multiply by 2, we create an activation record for multiply by with the parameter x bound to the argument 2. We need to create dynamic and static links, which in this case both point to the global scope. So the dynamic link again is the reference to the calling procedure. So because we called multiply by from the global scope, the dynamic link links to the global scope. And the static link points to the enclosing scope. And because multiply by was defined in the global scope, that is also pointing to the global activation record. Okay. So we have this activation record for multiply by. It's got a dynamic and static link. It does its work, which in this case is executing this lambda, which returns a procedure object. And that returns back into the global scope where we define the name double to equal whatever that lambda is. So we come back in here and we now have a binding for double in the global scope. Then on the next line it says call that binding for double, so use that function and pass it the value 7. So we create a new activation record where the parameter y is bound to the value 7. The dynamic link here again points to the global scope because again the function call was done in the global scope. This was the activation record that was being used when we made that call, so that's where the dynamic link points to. The static link, on the other hand, well, the static link is supposed to point to the enclosing scope. And as we saw with the substitution model, it was important that that enclosing scope has this variable x bound to the value 2 in this case. But that activation record no longer exists, nor do any of the bindings in that activation record because they got destroyed because of how the call stack typically works. All of which is to say, if we have closures, that means that the activation records need to have unlimited extent. So extent is the period of time for which a variable has storage allocated to it. So if an activation record has unlimited extent, it will just persist for as long as something is referencing or pointing to that activation record. All of which is to say activation records in languages with closures like this can't be allocated on the stack. It all needs to be allocated on the heap. And we'll need a way of keeping track of all these enclosing scopes. And that brings us to the implementation view of a closure. So the term closure actually refers to the memory model associated with the procedure object. When we create a procedure, we're creating essentially a pair of pointers. The first pointer in that pair is to the function itself. So when we say lambda y here, the first pointer, and so it creates a pair, and the first pair points to this lambda itself. It's the information necessary for executing that procedure. So you can think of it as the list of all the parameters and the list of all the expressions. Okay, so it's the lambda text, so is the first pointer. And the second pointer in that pair is to the parent scope, or the referencing environment. Okay, and this contains the environment of the function at the time of creation. So again, in the case of this lambda was created inside multiply by, so the second pointer should point to multiply by. That means we can keep track of the parent scope with this lambda. So the procedure object that we're passing around is this pair of pointers. Again, where the first pointer points to the lambda itself, and the second pointer points to the enclosing scope. So the thing bound to double needs to be that pair. So instead of storing these free variables, we'll store a pointer to where they can be found, and then when we go to create our activation records, we should be able to open all this stuff up. So you can think of a closure kind of like an egg for a function, Right? When we say lambda, we're creating that closure, we're creating that egg, and it contains all of the information that we need. So we're moving that procedure object around in our code. That's where we're moving around. We're passing this egg from function to function. It contains everything that we need in order to bring that function to life. So later on, when we say double 7, for example, to actually apply that procedure or to invoke it, we open up that closure and we pull out all the information that we need, the lambda text and the enclosing scope and all of that. Okay, so let's see that. So we'll do the same thing this time that we did before. We'll create activation records for each different function instance, but this time, instead of using a stack like we had before, we'll use a heap, which is just sort of an open space. Rather than having all our data aligned, we'll have it stored wherever it fits, and then we'll manually, or rather the system will manually keep track of all of the different references that it needs to. On a stack-oriented language, typically speaking, the active frame is whatever is on the top of the stack, at least how we've been drawing it. But we don't have that anymore. In the heap, everything's just sort of wherever it can fit. So we'll need to keep track of the active frame pointer as well. So this blue arrow here will represent which frame is the current one that's being executed. So we're currently in the global frame. We already have a binding for multiply by, so we can assert that we're on this line here. So we call multiply by with the value 2 and store the result in double. So when we call multiply by, that creates a new activation record somewhere else on the heap. So multiply by, where the parameter x is bound to the argument 2, and we need to create the static and dynamic references. So the dynamic link points to global because, again, multiply by was called by global, and the static link points to global, again, because the enclosing scope of multiply by. More details on that in a second. Okay, so once that's set up, once we have the activation record, we set that new activation record as the active frame, so our pointer goes there, and we execute the body of multiply by. So we walk through the details of constructing this lambda, essentially. So again, constructing a lambda creates this procedure object, which again is a pair of pointers. So when this is done, it returns that closure to the global scope, and it gets bound to the name double. So the active frame is now again the global scope, and we have a binding for double, and again that binding is a pair of pointers, and I've drawn them out here. Technically multiply by should have the same thing, but for the sake of keeping this drawing a bit cleaner, I've just done it for double because that's the one we're about to use. But so the thing that's bound to double is the procedure object as we've known it, just I've referenced it here as a pair of pointers. So this first one, this lambda symbol, refers to the text of the lambda. It's all the information like the list of parameters, the list of expressions in the body, all the stuff that we need to actually execute the function itself. And this other pointer here is a reference to the enclosing environment or the reference environment. So because lambda was created inside multiply by, when we ran this, we constructed this pair here in this scope. So we just took the current frame as this pointer, and then we returned it into the global scope. So it now points to a different frame. But when it was created, it would have been in this frame. So this pointer gets that information from the current frame, and then because we're returning it, it now gets bound in some other frame, but still references its parent. Now, because there is a reference pointing to multiply by, that is to say, if we can follow a reference from the global scope to this activation record, that means that activation record can't be garbage collected. If we're on a call stack, that's not really an issue. We can just get rid of all these activation frames as we see them, or as we leave them, rather. But when we're doing this on the heap, we have to actually maintain which activation records are good to be cleaned and which ones aren't. It's actually one of the main reasons why a garbage collector was added into early variations of the Lisp programming languages. So in this case, because we have a pointer pointing to multiply by, it won't get garbage collected. So because there's some way of referencing it, this is still useful. So what happens next, we've created this binding, and the next line says call double with the value 7. So again, create an activation record for double. So create a new activation record somewhere on the heap. And add in the dynamic and static links. So the dynamic link is again just the link of the calling procedure, so the current active procedure here. So the dynamic link points to global because we're calling double from global. And the static link is actually just a copy of this information. We open up the closure, we take this pointer, and we store it as the static link in this activation record. That way it points to multiply by, which is the enclosing scope. So it doesn't matter where this procedure object goes. If we run it in multiply by, it'll point to multiply by. If we pass it out to global and run it there, it'll still point to multiply by. If we pass it into some consuming procedure, like maybe that plot function that we saw before, the reference pointer would still point to the place where it was created. It's not going to change. So you can think of this essentially as an integer, an address value that will never change. So once we create the activation record, we open up that closure, we get the static information out of one of those pointers, and then the body and all the stuff that we need to know is in this other pointer, the lambda reference, if you will. Okay, so once we've done all that, we've created the activation record, we've created a dynamic link and a static link. The active frame then becomes double. We run through the body of that, and it in this case says times xy. So the x symbol, well, I'll start from y because it's probably the easiest. Y we find locally, right? We can just say the value of y is 7. If we want to know the value of x, though, we go looking locally. We don't find it in this activation record, but just like we did before, even when we were saying this was on a stack, even in the heap, if we can't find a variable locally, we follow the static link or the static chain out of this to the enclosing scope, and that leads us to multiply by, where sure enough, there's a binding to the value x. Similarly, if we're looking for this symbol here, this asterisk, what does that mean? We don't find a binding for asterisk and double. We don't find a multiply by either, so we follow that static link to global. We wouldn't find it there, and presumably, I didn't draw it in this drawing, but presumably there would be a static link to the primitive scope as well, which is sort of the last or the bottom scope. And that's where all those bindings for plus and times and all those would be. So we'd follow that eventually. So out of this static link, out of that static link, and then if necessary, we continue on until we either run out of static links or we find the symbol we're looking for. So to review real quick, a closure is a pair of references. So the first value in that reference is the lambda itself. The second value, the second pointer in that pair, is the reference to the enclosing scope. So in this case, multiply by, because lambda was defined, or rather executed, in this multiply by. So closures are pairs of pointers. When we go to create the activation records, we can open up that closure to get all the information we need, including the static reference as one of those two pointers. I think that about sums it up for this video. So I think that's also the end of this chapter. So in the next chapter, we'll move on to talking about some data structures or data abstractions, specifically talking about pairs and lists. And that's it. So I'll see you guys in the next video.